Hello everyone, this is Dr. Zach. It is time to recognize when U substitution is used to determine your antiderivatives. Let's begin. So your lesson preview was a reminder that you had to use the Ching rule in order to find the derivatives of these two functions. Now I'd like you to imagine for a minute if we are going to go backwards and find the antiderivative of our functions. We already know that the answer is going to be y equals the cosine of 6x to the fifth power plus c. However, we need to be able to figure out how to get back to these original functions. So what we'd like to do is recognize which antiderivatives we actually know. We know the antiderivative of u to the n du. We know the antiderivative sine of u du. We know several different trig functions. We even know what the antiderivative of e to the u du would become. So as we look at example 1, notice the parentheses are grouping your 3x plus 2 together. This was a composition of functions. So we're going to allow u to be equal to 3x plus 2. Now, if we use substitution in order to let u equal 3x plus 2, notice we're left with dx in the problem. What we'll do next is figure out the differential of u with respect to x. And we see that du is equal to 3 dx. If we solve for dx, we'll get du over 3. And now we can substitute. We have u squared times du over 3. Now the over 3 is annoying, so we're going to pull the 1/3 out front and be left with u squared du. So you know the antiderivative of x squared. The antiderivative of u squared is done similarly. U to the third over 3. Don't forget your plus c. Now we're not finished with our problem. So we're going to substitute next to rewrite our problem as 1/9 times the quantity 3x plus 2 raised to the third power plus c. So in order to complete these problems, you must know your basic antiderivative rules. That's why we've been practicing. And you're going to do u substitution to simplify these complex problems. As I'm looking at example 2, now I know the antiderivative of the sine. This one, though, has an angle that's a bit more intense. So if we were to let u equal the angle phi minus 2 theta, du is going to be equal to negative 2 d theta. Let's see how this helps us. When we rewrite our problem with the antiderivative, the sine, replacing 5 minus 2 theta with u, you'll notice you have to get rid of this d theta. But what does d theta equal? D theta is negative 1/2 du. So we're going to replace d theta with negative 1/2 du. Factor that negative 1/2 out of the problem. You're left with the antiderivative of the sine of u du. And of course, the antiderivative of the sine of u is going to be your negative cosine u. Don't forget plus c. Clean it up a little. We have 1/2 cosine. Replace the u. Go back to your original declaration of 5 minus 2 theta. And then we'll have our plus c. So this is called u substitution. You only know a certain number of basic antiderivatives, and you want to make your new problems look just like the basic antiderivatives so that you can integrate. So u substitution is used to change the variables to turn an unfamiliar integral into one that we can integrate. We're going to let u equal some function g of x and then determine du. Afterwards, do substitution. If you're solving an indefinite integral, it looks like f of g of x times g prime of x dx and then you replace your u, which is equal to your g of x, so that you can simplify your antiderivative. Now, if we're doing a definite integral, you have two choices. You can keep the substitution and also substitute those endpoints, or you can replace your u back into the integral. It's going to be up to you, and I'll explain that further when it's time. So as we examine example 3, notice I have 1 over the cosine squared. Well, we know 1 over cosine squared can be rewritten as a secant squared, keeping that angle as 2x dx. Now I know the antiderivative of secant, but I don't know the antiderivative of secant 2x. So that's what we're going to let u equal. U equals 2x, du is 2 dx. Solving for dx gives us du over 2. Rewrite the problem. 1/2 antiderivative, secant squared u du. Now, what was the antiderivative of that secant squared? You should know that was the tangent of u plus c. Do not forget to replace your u with tangent 2x plus c. Okay, so now example 4 is very complex. I have 2 parts to this problem, tangent x, secant squared x. If I allow u to be equal to the secant squared x, then what happens? Du equals, using a chain rule, 2 secant x times the secant x tangent x dx. That got really complex. And when I solve for dx, my goodness, du over 2 secant squared x tangent x. This looks like crazy talk. All right, so let's start again. So let's let u equal the tangent of x. Then du would equal the secant squared x dx. Ooh. So now dx, if we were to solve it, is du over secant squared x. Let's go back and look at this problem now. Don't worry about the endpoints. The tangent x was replaced with the u. Secant squared x is still in the problem, but dx is replaced with du over the secant squared x. Look what conveniently cancels out so that we're left with the integral, don't worry about those endpoints, u du. All right, so the right substitution in this problem was u equals tangent x. Now, let's think about these endpoints. We've been working with endpoints. When we have pi over 4, that's an x value. 0 is an x value. These terms say u. They are u values. It would be, you have 2 choices. You can find the antiderivative, u squared over 2 plus c. Don't need my c since it's a definite integral. And then replace these values with x equals 0 and x equals pi over 4 after you've replaced the u. So tangent of x quantity squared over 2 can be evaluated from 0 to pi over 4. And you, of course, are going to end up with, this is equal to 1/2. Now, a second option is that we could keep the values of u in the problem, but replace them. Let's see here. When x equals 0, u was equal to the tangent of 0, which was 0. So this new 0 is a u value. And when x equals pi over 4, u equals the tangent of pi over 4, and that, of course, is 1. So now when we integrate, we get our u squared over 2, and we can evaluate 0 to 1, which again gives us 1/2. So it does not matter which substitution you do. As long as you keep track of whether or not the endpoints are u values or x's when you substitute. All right, so I have a couple problems I want you to try with u substitution. 14, 22, 24, 30, 32, 38, 40, 50, and 52. Give these a try and then check through your answers. For number 14, you should probably let u equal 2t to the fourth plus 3. Number 22, u equals 1 plus x to the fourth. All right, now number 24 was not a u substitution problem. You have to use algebra to rewrite the problem, then you can integrate. Number 30, break the problem up just like I did with number 32. Let u equal x to the third minus 1 for number 32, then substitute and integrate. For number 30, you want to let u equal your x squared minus 8x plus 1. So then du is going to be 2x minus 8 dx. Then you'll be able to find dx. Example 5 is time to do a little bit trickier problem. For this problem, you have the square root of 2x minus 1. That's the value we're going to let u equal. So u equals 2x minus 1. Du equals 2 dx. All right, so when we substitute, we have the antiderivative x plus 1 times u to the 1/2 power. Dx is replaced with du over 2. Now you see that we have this extra x in here. That is definitely a problem. But go back to where you made your u substitution. You can solve for x so that you'll get u plus 1 divided by 2 is equal to x. Substitute that into our antiderivative now. We will get u plus 1 divided by 2 plus 1 multiplied by u to the 1/2 and du over 2. All right, a little bit more simplifying for this one. We have 1/2 the integral u over 2 plus 1/2 plus 1 multiplied by u to the 1/2 power du. To use your distributive property, we have 1/2 the antiderivative u to the 3/2 over 2 plus 1/2 u to the 1/2. Oh, let's make that 3/2. This is du. Then we're ready to integrate. 1/2 u to the 5/2 multiplied by 1/2 multiplied by 2/5 plus 3/2 u to the 3/2 multiplied by 2/3. Don't forget a nice plus c in here. Afterwards, we're going to clean it up a little bit more. 1/2 times 1/5. Remember, u gets replaced with our 2x minus 1 to the 5/2 now, plus 3/2 times your 2x minus 1. And when we multiply that by 2/3, it's actually 1. And don't forget plus c. All right, so example 5 proved to be a little bit more hardy. Okay, so give these next problems a little bit more practice. Number 50 follows what we did for example 5. And number 52 might also follow what we did for example 5. Once you've given these a little bit more practice, on page 301, try questions 9 to 54, multiples of 3. You don't have to do them all, but you should know how to do them. It gives number 79 a thorough try. All right, guys, you have a fabulous day.